All right, we'll take a look at number 21 here on our review. In this problem, we want to solve the following polynomial inequality algebraically. Express your solutions in interval notation. So as we look at this inequality, we've got a degree 3 cubic inequality. Our work is to find what we call the critical values. All right, and the critical values are the zeros, right, of the polynomial. So the zeros of the related equation. So for right now, let's go ahead and find the zeros, this polynomial inequality. Let's go ahead and form the related equation. All right, so as I form the related equation, I get 2 times x plus 1 squared times x plus 7 equals 0. And with any higher degree polynomial, I'm always trying to factor. And this one's already factored for us, right? We've got a degree 3 polynomial, which means it has 3 linear factors. The x plus 1, that linear factor is being used 2 times. And the x plus 7 is being used once. So as you're talking about the zeros, right, we've got 2 different zeros. Right, there's 2 different factors being used of x, so all zeros come from linear factors of the form x minus 0. So we can look at it and see the zeros without even having to do any work. But we'll go ahead and finish it down here, solve it out. So I get -1 and -7 for the critical values. So with that said, you can look at these critical values and form your test intervals. So in this problem here, again, the critical values are the 2 numbers -1 and -7, the zeros of the related equation. So with these being zeros, if you were to graph this polynomial, it's degree 3 cubic, these will be the x-intercept locations. Now with our inequality, we have a less than problem. So I want to make note of that. With it being less than, right, we're not going to include -7, -1 as solutions. Because we know -7, -1 make it equal 0. We want to be less than 0. So again, our next step after we form the critical values is to set up the test intervals. Alright, so let's go ahead and do that. So we have a possibility of solutions for all the values of x less than -7. So -infinity, -7 with a parenthesis is a possibility of solutions. Or we can have the values of x greater than -7 and less than -1. All right? Or we can have the values of x greater than -1. -1 to infinity. So my 3 regions. Well, my third step in solving this algebraically is to test. Pick a test value. Pick a number from each interval. Something easy to work with. Let's test with -8. -8 is a nice easy integer to work with. It's less than -7. Maybe -2 for the interval from -7 to -1. Something easy to plug in, work by hand, simplify. And anytime I can use 0, I like to use 0. So I'll use 0 for that one. So is -8 a solution? So as we test this first interval, right, let's go ahead and plug in -8. Well, as we plug that in, that's 2 times -8 plus 1 squared, right, times -8 plus 7 less than 0. So again, out went x, right, and then came the test value of -8. As we simplify, well, we get 2 times what? -8 plus 1 is -7. -8 plus 7 is -1. Is that less than 0? As we simplify down, that's 2 times 49, -7 squared, times -1 less than 0. And 2 times 49 is 98. 98 times -1, that's -98. Is negative 98 less than 0? It is. It checks. It's a solution. So that means all values of x less than negative 7 are in the solution set. Now let's go on to our next interval. Let's test it. How about negative 7, negative 1? Well, let's plug in our test value. So 2 times negative 2 plus 1 squared times negative 2 plus 7, is it less than 0? Well, as we simplify down, that's 2 times negative 1 squared. Negative 2 plus 7 is 5. 2 times negative 1 squared is 2 times 1 times 5. 2 times 1 times 5 is 10. 10 is greater than 0. Not a solution. Does not work. And then our third and final possibility to test, right, is negative 1 to infinity. So let's test it. So negative 1 to infinity, as we test, I'm going to test with 0. So that'll be 2 times 0 plus 1 squared times 0 plus 7 less than 0. Well, as we simplify that, 0 plus 1 squared, that's 1 squared, times 0 plus 7 is 7. That's 2 times 1 times, that's 14. 14 is greater than 0. It doesn't work. Must throw it out. So our solution set, right, is one interval. Our solution set is all the values less than negative 7. So negative infinity to negative 7. Writing it in interval notation. So you only need one number. If one number works, they all work. If it doesn't, and none of them do. And then you can check it, of course, graphically also. You could use your leading term test and use your knowledge of zeros and multiplicity and sketch that polynomial. Right? But that's a way to look at it algebraically without having to tie into graph. So again, you can graph in your calculator too, and you'll see the graph of this cubic polynomial is negative. It's on the negative side of the y-axis, on the left side of negative 7. So it'd be a good thing to do is to graph it and check it, to look at it there and check out your solutions. So take advantage of that. Do look at it graphically if you get a chance. All right, moving on. Let's do another inequality. This was a rational inequality. So we just solved a polynomial inequality. Well, the only difference this time with our critical values, all right, is we're still going to be looking for the zeros of the related equation. So you're still going to have to solve the equation, find the zeros, and add to it any undefined values. So here's the difference with rational inequalities. Right? We have the possibility of undefined values. That would be my first step. X plus 3 cannot equal 0. So that implies x cannot equal negative 3. So negative 3 is a critical value. Right? That's an undefined value. You want to make note of that. So we'll make note of that here on the side. All right. So with a rational function like x plus 18 over x plus 3, that's the revocation of your vertical asymptote of negative 3. So your graph break apart negative 3. You say break in your graph. It goes vertical there. All right. Now we found the undefined value. Let's find the zeros. So I'm ready to move on to my next step. So finding the zeros, we're going to take our rational, x plus 18 over x plus 3, and forget about less than or equal to. Let's set it equal to 6. As we're doing that, we're solving a rational inequality. So let's multiply by the least common denominator. So we'll go ahead and introduce the LCD. So we make note of that. Our least common denominator is x plus 3. So again, clear the fraction. So as we do that step, what do we end up with? We end up with what? The x plus 3's divide out. So we get x plus 18 equal to 6 times x plus 3. As we simplify here, that's 6x plus 18, right? And then we want to go ahead and solve for x. Say linear equation. Let's go ahead and get x by itself, right? And so let's do that. So with that, go ahead and subtract the x, get the x terms together. All right, and then we'll go ahead and move the 18 over, subtract it over to the other side. So as we do that, we end up with x minus 6x, which is negative 5x, equal to 0. As we divide out negative 5 on both sides, x equals 0. All right. So as you're looking at that, right, we've got our other 0, or the critical value, right? And you check it, right? If you were to plug 0 into that, what's 0 plus 18 over 0 plus 3? That's 18 over 3, or 6. So you see that is a solution. But that's a critical value. So negative 3 and 0. So 0 again, that's a critical value for my rational inequality. So let's go ahead and set up our test intervals. So now that we have our critical values, ready to move on to the test intervals and figure out what our solution set is going to be. So let's go ahead and build our x line. So all real numbers x, negative infinity to positive infinity. We've got two critical values. We've got negative 3. And if you were looking at that graphically, right, that would be a vertical asymptote. That's an undefined value, so we're not going to include that number. And then, of course, we have 0. Now, 0 is a 0 of the function. It's an x-intercept location. So we are going to include that in this problem because of the less than equal to. So that's going to be important with our brackets. So as far as test intervals go, we're going to be looking at the left of the vertical asymptote, negative infinity, negative 3. We're going to be looking at the numbers between the vertical asymptote and the 0, the x-intercept, negative 3 to 0. And then the right side of the x-intercept, 0 to infinity. So now we're ready to pick our test values, right, and test them. So find your test values, right, and plug them in. So negative infinity, negative 3, I'm going to test this one with negative 4. I'm going to use negative 1, something easy to plug in. Here I'm going to use positive 1, easy number between 0 and infinity. So let's see if there's solutions. So with negative 4, let's plug it in. So we get negative 4 plus 18 divided by negative 4 plus 3. So out goes x, in comes our test value. And the question is it less than or equal to 6? Well, as we simplify down, negative 4 plus 18, that's 14. Negative 4 plus 1 is negative 1. So we end up with negative 14 less than or equal to 6. Well, that's true, it is. Negative 4 is a solution. So there's one of our intervals, right, in this problem. So we found a value there with that one. So we got to include that. So all real numbers less than or equal to negative 3. Now be careful. Somebody check me. On this next interval, I put negative 3 to 0. Now remember, 0 is a critical value. All right, say 0, say solution to the related equation. And since we had equality, we do need a bracket on that 0, so don't forget that. It's an easy mistake to make, right? We do need the bracket on 0 because of the less than equal to. And this problem making equal 6, when we plug in that number, that will be a solution. So let's go see if this interval here is part of the solution set. So we're going to pick a value. We said negative 1. So as I plug that in, I've got negative 1 plus 18 divided by negative 1 plus 3. Question, is it less than or equal to 6? Well, as we simplify that down, that's 17 over 2. Well, 17 over 2, that's what, 8.5? 8.5 is greater than 6. That didn't work. Exclude it from the solution set. And then our last region, let's take our last one. Plug in 0. So 0 plus 18 divided by 0 plus 3, is that less than or equal to 6? All right, well, as we simplify that down, and make sure we plug in the right number. Why am I plugging in 0? We picked 1, right, for our test value. So out went x, in went 1, not 0. So testing the interval numbers greater than or equal to 0. But as I simplify that, that's 19 over 4. Well, 19 over 4 is 4 3/4. Right? Well, 4 3/4 is less than 6. So it does check. So as we simplify that down, that's a solution, right, to this problem. So that means we got to include all numbers greater than or equal to 0. So our solution set, we've now got it. So here's our solution set. We'll go ahead and write in those two intervals. So all the x values less than -3, or all the values greater than or equal to 0. All right, just solve that rational inequality. All right, let's move on. Looking at our next topics, we get into studying rational graphs, being able to graph a rational function, finding these key characteristics, which are your asymptotes, which are equations of imaginary lines, vertical lines, horizontal lines, slanted lines. We're going to focus on two types of vertical and horizontal asymptotes that shape your graph. They give you shape to it. Your graph will go vertical if you have a vertical asymptote, and it'll flatten out horizontally with a horizontal asymptote at those locations. Then we have holes. They come into play with rationals, and of course, we always want to know the domain, the intercepts, some quick points to plot. Now, your first step in building your sketch of your rational graph is to make sure you simplify your rational function. So before you begin, go ahead and factor. All right, so as you look at the numerator, all right, we got a factor of 2 in both terms. So let's go ahead and factor out the 2. That'll leave me with x plus 1. And in the denominator, this quadratic trinomial, it factors nicely with integers. We need an x and an x up front for x squared. And we know the factors of 4 that work together to make -3 are 1 minus 4. So 1 minus 4 will build those two linear factors. Well, what happens when I do that? Well, as I factor the quadratic in the denominator, x plus 1 and x minus 4, we produce a common factor of x. So this function simplifies. So we end up simplifying down to 2 divided by x minus 4. Well, that leads you into your characteristics. So the first thing I want to talk about is, does your graph have any holes in your graph? And holes are points or ordered pairs at which your graph breaks. It's a point of discontinuity. It breaks your graph up at that point. And where the holes come into play, they come into play if you have common factors. Your holes are located at the zeros of your common factors. So in this problem here, we have a common factor, x plus 1. What is this 0? So we solve it for x, we get a 0 of -1. So that means we have a 0 at -1, which means we have a hole at -1. So we have a hole at -1 on our graph. Now I want to find the y coordinate for that hole. So what does y equal? Now to find y, we're just going to plug it into our function. Now do remember we simplified our function. So we find f of -1, that's 2 over -1 minus 4, right? We had 2 over x minus 4. So as we simplify that down, that's 2 divided by -5, or -2/5. So there's y. So that's what y equals. So our y coordinate, right, for x equal to -1, we know y is equal to -2/5. So there's your y coordinate. So going back to my ordered pair, -1 2/5, which is 0.4, right? That's a hole in your graph, right? And that's a -2/5. I check my sign, getting a negative. But -1, -2/5 will be a hole in it. So we'll plot that point. We're going to put a little open circle there as we begin to sketch in the graph. So that's one thing to make note of in this graph if you want to build it. Right? Those are characteristics you want to show. Let's start to look at what the sketch of this graph will do. So -1, -2/5, so left 1, down, -2/5 is a hole in it. So that's a point of discontinuity there at -1, -2/5. All right, now I want to move on. And we'll move on to my vertical asymptotes. So that's going to be my next step. We'll stick with undefined values. Holes are undefined values. Vertical asymptotes produce undefined values. And they come from the zeros of your denominator factors. So as we look at our denominator, after we reduced it, we have a factor of x minus 4. So that implies x equals 4. So the zero of our denominator is 4. So that means we have a vertical asymptote, which is the equation of a vertical line. X equals constant, and we can go graph that in. So over here at 4 on the x-axis, right, our graph is going to go vertical. So I'm going to draw an imaginary vertical line at that location. There's x equals 4. And that leads you to your domain. So that's one thing I want to talk about. Our domain is tied in directly with our holes and our vertical asymptote, because all the real number values of x that satisfy your function. So we have a break at -1, so all x values less than -1. And then we're going to continue between the hole and the vertical asymptotes, another break. So -1 over to 4, and then from 4 to infinity. So there's your domain of your graph. Right? So domain tied in directly, right, with those undefined values. So again, right here at -1, right, and at 4. There are breaks. All right, when I add to our characteristics, let's move on to, do we have a horizontal asymptote? So we found there's a vertical asymptote, which means our graph will get closer and closer and closer to that vertical line x4, will get vertical. But it won't touch it because it's an undefined value. Now, horizontal asymptotes are not undefined values. Your graph can intersect the horizontal asymptote, and we will want to find that intersection if it has one. But to prove the existence of whether or not you have a horizontal, you might not, you got to compare the degrees of the two polynomials you're dividing. For instance, let's let n be the numerator degree. Now, what is the degree? The degree of the polynomial is the exponent of your leading term, your greatest power. So we have a linear polynomial, 2x plus 2, degree 1 polynomial. And m, we'll let it be the denominator degree. So to abbreviate. And it's quadratic, so it's degree 2. So as you compare these two degrees, all right, so that implies n is less than m. Well, that implies a horizontal asymptote exists. A horizontal asymptote exists if n is less than m or n is equal to m. And where it exists, when n is less than m, will always be at the x-axis. The x-axis, the line y equals 0, will form your horizontal asymptote. So if you go back up here, you draw in, I'll dash it in here in blue. The line y equals 0, the horizontal asymptote. All right, and then moving on, let's go ahead and get some quick points on our graph. All right, and one thing I want to do is go ahead and list the intercepts. So as we talk about x-intercept points, these are quick points to get. Now, x-intercept points, where your graph crosses the x-axis, are your zeros you function. So it's when your function equals 0. So if you look at this function, which we had 2 over x minus 4 equal to 0, well, what happened? As we solved that for x, right, we get 2 equal to 0, which is not true. So there is no 0, right? Which means there's no x-intercept. This graph will never cross the x-axis, which also concludes that our graph will never touch this horizontal asymptote because it is the x-axis. So this is a graph that has no no x-intercept. Now our y-intercept, does the graph cross through the y-axis? Well, that's a quick, easy one to get. All we got to do to find that is find out what f of 0 equals. Take out x, right, and let it equal 0. So what does f of 0 equal? Well, that's 2 divided by 0 minus 4. As we simplify, that's 2 over negative 4, or negative 1/2. So 0, negative 1/2 is our y-intercept point. So yes, it does cross through the y-axis right here at 0, negative 1/2. All right. Now, based off that, I already know the left side of my graph. So I know this graph flattens out horizontally, never touches the x-axis. Horizontal asymptote shapes your graph. Has a hole at negative 1, negative 2/5. Passes through 0, negative 1/2. And then what happens when it gets to 4 on the x-axis? It goes vertical. So there's your left side of this graph. And then to find the right side of your graph, I need to do a little more work. For example, I need to pick a point for, like, for example, what's 5? Let's find a point here on the right side. What does f of 5 equal? That's 2 divided by 5 minus 4, which is 2 divided by 1, or 2. So f of 5 equals 2, so that implies 5, 2 is on our graph. So I could plot this point, 5, 2, and now I can sketch the right side of our graph. Flattens out horizontally at the x-axis, goes vertical at x equal to 4. And there's your sketch of that rational function. So you can see how I use my asymptotes, my intercepts, my holes, that's this one had, to build the sketch of this graph. All right, let's move on. Let's do number 24. Another example, same topics. See if we can sketch the graph of its rational function. First step, let's go ahead and factor. Need to go ahead and try to reduce this function and simplify it. So we have two quadratic trinomials, and both of these factor nicely with integers. We know x squared plus 2x minus 3. Well, we know the factors of 3, 1, and 3 will work together to make 2. That'll be a plus 3 and a minus 1. Denominator, we got x squared plus x minus 6. We need x and x up front. What factors of 6 make the middle term coefficient of 1? We need a plus 3 and a minus 2 on that one. So again, you see as we factor it, right, what happens? We produce a common factor again, just like our last example. So it does reduce, it does simplify down to x minus 1 over x minus 2. So there's our function f of x. Now that leads us directly to our characteristics. So as we move to talk about holes, remember the holes are the zeros of the common factors. And we only have one, right? We only have one common factor in this problem, that's x plus 3. And when does that equal 0? When x equal negative 3. So we're going to have a hole at negative 3 on the x-axis. Now we've got to find the y-coordinate. So let's go ahead and plug that in. So what does f of negative 3 equal? It'll be negative 3 minus 1 over negative 3 minus 2. And as we simplify that, we get negative 4 over negative 5. So y is equal to 4/5. There's the y-coordinate. So our hole will be at the ordered pair, negative 3 4/5. So we can begin to sketch in this graph. So let's go ahead and start to look at it. So we'll go ahead and build our x and our y-axis. So at negative 3 4/5, left 3, up 1, we have a hole right here. Alright, so go ahead and graph in that hole there, that ordered pair. And now let's add to it. Let's go ahead and talk about any vertical asymptotes. So there are any imaginary vertical lines that are going to shape this graph. And remember, to find those, we're looking at the zeros of the denominator factors. So we got a factor of x minus 2. And yeah, x minus 2 equals 0 and x equals 2. So that means we have a vertical asymptote at x equal to 2. So as we go plot that over here. So here's 2 on the x-axis. I'm going to draw in this imaginary vertical line, which what will happen with our graph, it's going to go vertical at that location. And again, remember, that ties in directly, as now we can talk about our domain. So remember, the holes in the vertical asymptotes are a list of the undefined values. So we break at -4 and 2, or -3 and 2. So the hole's at -3. So we'll see our domain to the left of the hole, -infinity, -3. We'll see it take place from -3 to 2 between the hole and the vertical asymptote, and from 2 to infinity. There's your domain. Alright. And moving on, let's go to our horizontal asymptote. Alright, and our horizontal asymptote, remember, is we're comparing the degrees. We'll see if our graph flattens out horizontally anywhere. And remember, when we compare the degrees, I'm going to abbreviate again, just like I did in the last example. N being the numerator degree. This was a quadratic polynomial. And m, denominator, was another quadratic, 2-degree 2 polynomials. So as we compare those, n is equal to m. Well, if n is less than m, it flattens out at the x-axis, y equals 0. If n equals m, we also have a horizontal asymptote. And where it exists is the ratio of the leading coefficients. And those are both 1, right? Again, the leading coefficients. So we'll go ahead and make note of that. So that means we have a horizontal asymptote at what? Y equal to 1. So y equal 1. So at 1 on the y-axis, our graph's going to flatten out horizontally. So let's go ahead and graph that in here. So at 1, here's 1. We'll draw in this imaginary horizontal line. It's going to shape my graph. It's going to give me a picture of it here in a little bit. And one thing you might want to go ahead and find right now, let's just go ahead and get our intercepts. So what's our x-intercept points? Just graph across the x-axis. So when does our function equal 0? So that implies when does x minus 1 over x minus 2 equal 0? Well, as we multiply both sides by x minus 2, right, as we clear the fraction, it's x minus 1 equal to 0, which implies x equal 1. So we're going to have an x-intercept at 1. So there's our x-intercept point. The ordered pair 1, 0. We can go ahead and plot that point. So our graph's going to pass through that ordered pair. All right? So that's our x-intercept. So it's always the zeros of your numerator. In a rational function like this one, right, our numerator 0, the fraction is going to equal 0. How about y-intercept point? Let's just graph cross through the y-axis. Well, what we're going to do is take out x and plug in 0. What does f of 0 equal? So f of 0 equals what? 0 minus 1 over 0 minus 2, which is -1 over -2, which is 1/2. So our y-intercept is going to be at the point 0, 1/2. That's our y-intercept point. So we can plot that point. So right here on the y-axis, right here at 0.5, right, we have a y-intercept. Now with all that information, it can begin to graph this function. Now one thing I do want to make note of is this horizontal asymptotes at y equal 1. So remember, this is not an undefined value. So let's see if it intersects the horizontal asymptote. Is there an intersection point with the horizontal asymptote? Always look for that. And to find that, we just set it equal to what? Horizontal asymptote's at 1. So does x minus 1 over x minus 2, will it equal 1? That's where our horizontal asymptote is. And as we solve that, well, we can go ahead and solve that. We'll clear out our fraction. Multiply both sides by x minus 2. As we do that, we get x minus 1 equal to x minus 2. As we solve for x, what happens? We get a statement that's not true. So, no intersection. So, no. So, it does not intersect, which now makes it even easier to sketch my graph. So over here, as we build in the graph, we know it's going to flatten out at y equal 1. Never going to touch it. It can't ever intersect this horizontal. We just determined that. So based off our hole and our y-intercept and the x-intercept, we can go ahead and graph in, right, the right side, or I'm sorry, the left side of this function. So there's a sketch of the left side. Now again, I would need more information to graph in the right side. So for example, let's find a quick point like 3. What happens at 3? What's f of 3 equal? Well, that's 3 minus 1 divided by 3 minus 2, which is 2 over 1, or 2. So that's a y value. So we got the ordered pair of 3, 2. Our graph passes through it. So as we plot 3, 2, be up here on the y-axis, or up here on quad 1. Now we can graph in. So based off the vertical asymptote and the horizontal, here's the right side of our graph. So we've sketched it using that information. All right. Moving on, let's go to problem number 25. All right, let's talk about a polynomial of higher degree. Let's state the leading term and the end behavior of the following polynomial. Find the zeros in multiplicity and tell me the behavior with multiplicity of the graph, which means does it touch or cross through the x-axis of those zeros. And then sketch it based off that information. So one thing nice about this polynomial is they've done the work for us, and now we're going to find the zeros, right? It's already been factored for us. All right, so if you wanted to, you can go ahead and show in these linear factors. I got negative 6 times x squared. Well, that's x times x minus 7 times x plus 1 cubed, which is x plus 1, times x plus 1, times x plus 1. So if you look at this, what degree of this polynomial? We've got what? We got 6 linear factors. All right. So remember, if we have 6 linear factors, we have a degree 6 polynomial. All right. So let's talk about leading term. So our leading term, right, would be the term, again, up front leading this polynomial, and if it was in standard form, it's our term with the greatest power. So if we have a degree 6 polynomial, we know our leading coefficient is negative 6. Our leading term is going to be negative 6x to the 6th power. So if we multiply those 6 linear factors together, we're going to get x to the 6th term. That's going to be our greatest power term. So there's our leading term. So let's use the leading term test. So a little review. Leading term test. Well, leading term says find the degree of your polynomial. And the degree of your polynomial is 6. And that's a even degree polynomial. And our leading coefficient. Let's talk about our leading coefficient. Our leading coefficient is negative 6. Well, based off leading term tests, even degree polynomial and a negative leading coefficient, right? That means our graph is going to have this behavior. Left end is going to go to negative infinity, and the right end is going to go to negative infinity. So left and right tail always go the same direction with even degrees. Negative, they go down. Now this middle behavior, I don't know. That's why I draw these squiggly lines. So there's the end behavior. So the end behaviors, they both go to negative infinity. Right? So if it's an odd degree, they go opposite directions. Right? They're odd degree. One goes up, one goes down. Positive coefficient, it's left tail down, right tail up. And if it's negative, left tail up, right tail down. But if they even, they both go up, it's positive coefficient. Both go down to negative. Now, while we're at it, let's go ahead and mention the zeros. So I'm going to talk about the zeros of this polynomial. So our zeros come directly from our, what? Let's put this over here where we can see it. All right, so our zeros come directly from our linear factors. All right, so, and with that, we're going to look at the multiplicity right beneath it. Put that with it. So as we look at this first factor, we get a 0 of x equals 0. So again, our zeros, we take each factor and set them equal 0. So x equals 0. We know we have a 0 of x minus 7 equals 0, which implies x equals 7. Right? We know that we get a factor of x plus 1. That equals 0 and x equals negative 1. So x equals negative 1 is 0. So we have 0, 7, and negative 1. And the zeros from those three linear factors. Now the multiplicity is the number of times that factor occurs. That factor is being used. So with x equals 0, right, we had 2 of its factor squared. Multiplicity is 2. The x minus 7, we had 1 of its factor. X plus 1, we had 3, which produces 0, negative 1. And you can add those up in an equal degree polynomial. Now here's where our behavior comes in. So if we have a 0, all right, that means we have a x-intercept at the origin. Well, since this is even, our graph will touch that x-intercept. So again, we'll write the x-intercept above it. 0, 0 will be the x-intercept, and it'll touch that and bounce off it, form a turning point. Now with this one, we're looking at an odd multiplicity. So that means instead of touching it, it's going to cross through it. All right? So at the point 7, 0, which will be an x-intercept, it's going to cross through the x-axis. All right? So again, these zeros tell us our x-intercepts. And we know negative 1, 0 is going to be an x-intercept. And since 3 is an odd multiplicity, it's going to be crossing through. It crosses through the x-axis. So with that said, let's use our information and graph it. So we want to graph in, and we can build our x and y axis. Now with our information, we can sketch in a pretty good look of this graph. So let's put in information. So we got negative 1 as a 0. We got the origin as a 0. And then we got 7 over here as a 0. So these are x-intercepts. Negative 1, 0, 0, 0, and 7, 0. And based off leading term tests, right, we know that the left end of our graph, right, goes down to negative infinity. All right, so I'm going to start in the sketch. Now what happens at negative 1? It's going to cross through at negative 1. So when you draw on your graph, right, we're coming from negative infinity, it's going to cross through that, but then it's going to come back down because we have a 0 at 0. And here's the difference now. It touches here and doesn't go through it because it had an even multiplicity. And then it comes back down over here at 7, crosses through. And remember, our left tail and our right tail both go to negative infinity. But there's a sketch of that graph based off that information. Right? So using our leading term test, using our zeros and multiplicity, we can get a quick visual of the polynomial of higher degree. All right, so we'll stop there and continue on here a little bit.